Redshift. So this video, as promised, about redshift. Now, before we look at redshift, let's look at the Doppler effect. If there's a car on the left which is producing a note, its engine is making a noise, and the circles represent the sound waves coming from the engine. Now, the car on the right is moving, and because it's moving, you can imagine it kind of catching up with the waves in front of it, and the waves behind it, it's leaving them behind. As a result of this, if a car's coming towards you, then the note that you hear would be a higher pitch. If a car's moving away from you, then the note that you would hear would be a lower pitch. I'll do a little impersonation now. And that was a car going past me, actually. It wasn't, I did it. Anyway, the frequency of the sound heard, in other words, its wavelength, depends on the velocity of the car relative to the observer. And the wavelength is bigger if the object is moving away from you. Now, that happens with sound. It also happens with light from distant galaxies. This is the spectrum of light from the sun. And as you would expect, there's Roy G. Biv, but there's also these black lines. And these black lines, it's called an absorption spectrum. And these black lines are caused by elements in the atmosphere of the sun, in the photosphere, absorbing definite wavelengths. And by measuring these wavelengths, we can actually work out the composition of the sun or any star. Okay, the wavelengths of the lines are characteristic, like a barcode, of the elements present. Now, look at these two spectra. The first one is a nearby star, and the black lines are where we would expect them to be. Then we look at a star in a distant galaxy, and the black lines are still there, the barcode is still there, but they appear to be in the wrong place. The wavelengths are bigger than we would expect. They have been shifted towards the red end of the spectrum. They have been redshifted. And why have they been redshifted? Why are the wavelengths bigger? Because just like in the Doppler effect, the galaxy is moving away from us very fast. And by measuring the change in wavelength, we can calculate its recession velocity. By measuring the redshift of the light from a galaxy, we can work out how fast it's moving away from us. And so we get to Edwin Hubble. And Edwin Hubble looked at lots and lots of galaxies. He measured how far away they were. I mean, the first amazing thing he discovered is that there is actually more than one galaxy, and these little spirally clouds in the sky were other galaxies. He measured their distances using standard candles, and he worked out their recession velocities using redshift, and he discovered a very interesting pattern. He plotted a graph. And looking at this graph, recession velocity against distance, what Hubble discovered is that galaxies further away from us are moving away from us faster. There's a positive correlation between the relative velocity, the recession velocity and their distance. His points were kind of showed the correlation. As we've managed to take more and more accurate readings of recession velocity and distance, the points have got closer and closer to the line. Hubbles Law says that recession velocity is proportional to distance. In other words, V equals h naught times d, and h naught is called the Hubble constant. Now, all galaxies are moving away from us, apart from a very small number next to us. You know, the other 200 billion galaxies are moving away from us. We're not special. They're actually all moving away from each other. And if they're all moving away from each other, that means in the past they were closer together. And that must mean that the universe is expanding. The universe is getting bigger. Okay? And using Hubble's graph, what we can do is we can figure out when they started moving away from each other. In other words, we can work out when the Big Bang happened. And you can work this out from, it's the inverse of the gradient of Hubble's graph. It's 1 over h naught. If you imagine velocity is distance over time, then time is distance over velocity. So that's 1 over the gradient of the graph. So the age of the universe is 1 over the Hubble constant, which is 13.8 billion years, according to the internet, and I just had a look. Interesting that the Hubble constant is changing all the time as the universe gets older. Now, a lot of people, when it first came out, didn't accept Hubble's theory of the expanding universe. However, some more evidence exists that the universe used to be much smaller and much hotter. If you imagine the universe a long, long time ago, the universe was much smaller, much hotter, much more uniform, like a plasma of subatomic particles, very, very hot. The universe now is made up of stars and galaxies and stuff, dark matter, dark energy, which we don't know a huge amount about, but basically it's much, much colder, it's bigger, and it's more spread out. It is coagulated somewhat, it's kind of bunched together. Now, when the first atoms formed, which was about 300,000 years old, the universe, a very early universe, the space between these atoms was filled with ultraviolet radiation. As the atoms could absorb and emit radiation, the space between them was filled with ultraviolet radiation. And that radiation is still here in the background. Much of this radiation remains. It's not ultraviolet anymore. It's been redshifted and now it's microwaves. It can be detected in all directions in space, and we call it CMBR, Cosmic Microwave Background Radiation. Cosmic, as it's in the cosmos, it's microwave, it's in the background, and it's radiation. Okay, NASA and others have detected CMBR in all directions, and by doing that and mapping it, it's giving us a good idea of how the early universe was in terms of the distribution of the mass and temperature in the early universe. And looking at this diagram, which I believe comes from a satellite called WMAP, it shows us that even then, when the universe was 300,000 years old, there were hotter bits and colder bits. There were temperature variations. It wasn't perfectly uniform.